I'm going to show how to use an interactive simulation for a liquid phase reaction that takes place in a plug flow reactor. And what we're going to calculate and what's shown in this figure is the molar flow rate of the reactant A and the reactant B and the product C as a function of cumulative volume. So you can think of this as distance down the reactor multiplied by the cross-sectional area of the reactor. And the simulation allows us to change the fraction of the feed, that's component A, the rate constant for the reaction, and the reaction order with respect to B. So the reaction order with respect to A is first order, but for B we can change the order. The simulation is located at this link shown here in blue. And so let's look at this simulation. So the simulation, if we change the reaction rate constant and increase it, then the flow rates of A and B decrease as a function of distance down, and the flow rate of the product C increases. If we change the reaction order with respect to B, so it's second order, then you'll notice that the flow rate of B doesn't decrease as fast, because as we lower the concentration of B, the rate slows down even more because it's second order. You could also make the reaction order zero order in B, and let's spread this out a little bit, lower rate constant. So now what happens, if it's really zero order, then all the B can react. And, it's 2B versus reacts with 1 mole of A, and the mole fraction of A is 1/2, so it's not a stoichiometric feed. So we use up all of the B, and then reaction stops. Well, in a real reaction, as that can be zero order at higher concentrations, as the concentration of B gets low enough, it's going to convert to first order, so it's not going to go all the way to zero as shown in this simulation. You can also change the mole fraction of B, and to make the mole fraction lower, now somewhere around here, we're close to stoichiometric, 2 moles of B for every mole of A in the feed. The equations used to generate the differential equations are shown in the details here. And since this is a liquid phase reaction, the mole change doesn't come into consideration in calculating the molar flow rates, the reaction rate. If this was gas phase reaction, it'd be a different situation.